Hey Calc, welcome back. Hope you all are well. Welcome to Unit 6. This is our last unit before we start reviewing. So this should take us up until about spring break, and then we'll have lots of time to review before the AP exam. So go ahead and double check the checklist. Our objective today is going to be to find the area between two functions. So we've already found the area between one function and the x-axis. This time we're going to be looking between two functions. We're going to do this both by hand and with the calculator. So I'm going to show you both ways, and you'll have a bit of both on your homework as well. So I'm going to go ahead and force a pause on the screen. You know what to do from here. All right, so I don't need you to write anything yet. I just want to look at the old kind of problem before we look at the new kind of problem. So this is what we had been doing, right? I give you some kind of function. I say, can you find me the area under the curve? And that means the area between the red graph and the x-axis, right? So I'd first need to find like where this graph intersects y equals 0 or the x-axis. You can probably tell if you set this equal to 0 that your x-intercepts would be plus or minus square root of 2, right? And so when I set up the integral, remember the integral is an elongated s for an infinite sum from, I'm going to go ahead and put the x equals here, from x equals negative square root of 2 to x equals positive square root of 2. And then I would have f of x dx here, right? And the f of x represents the height of each rectangle, right? So if I take like one representative here, I grab that rectangle. The height is whatever the y value was right there, right? And then the width is this infinitesimally small dx, right? If I were to grab a different rectangle like this one, the height of that rectangle is still whatever the y value was for that x, f of x, right? And the width is this tiny, this really super thin dx, okay? So this represents the area under the curve between the function f of x equals 2 minus x squared and the x-axis. A couple ways we could do this, right? We could antiderive this function and then plug in square root of 2 and negative square root of 2. If it were calculator active, I'm done. I can just math 9 this sucker, right? And we're going to be talking about same ways when we've got two functions as well. All right, so what about something like this? What about when I have two curves? And force pause on your screen. Can you go ahead and just a really rough sketch of the two functions that I have there, and then go ahead and label them correctly as well. All right, so we are back, and I went ahead and shaded the area that we're looking at. So it's the area enclosed by the two curves. Okay, so I'm still going to come back to this idea of filling in all that yellow stuff with an infinite number of rectangles. So I'm still going to take an infinite sum, so an integral. And now take a look, I'm still in terms of x, right? So take a look at the domain of the yellow part. So the domain, we go from x equals negative 2 to x equals positive 1. So I'm going to go x equals negative 2 to x equals positive 1. Now I need to figure out how I'm going to fill in this yellow piece with a whole bunch of rectangles, okay? So my rectangles are going to look like this. We're going to fill them in. Let's see if I can grab that pen. There we go. We're going to fill them in with all these little rectangles. So here's a rectangle, here's a rectangle, and we just keep filling these in with, and they have, you know, height that looks like it's dependent on both f and g, right? And then this infinitesimally thin base of dx, okay? So let's figure out a formula for each height, because you can tell the height varies depending on what x value I'm on, right? For example, if I grab this rectangle here, let me do it in red. Let's go. So here, let's pick out this red rectangle. Can you tell what the height is? So the height's going to be 2, right? Because it started at a y value of 1 and then went down to a y value of negative 1. So if I start at 1, go down to negative 1, that's a height of 2, right? 1 minus negative 1. You take the difference to get the height, right? Similarly, if I come over and let's grab this one here. Let's take a look at this rectangle. What is its height? It's also 2 because I'm taking the y value from the top function minus the y value from the bottom function, right? So 2 minus 1. So no matter what rectangle I'm looking at, let's grab like this one here. To get the height, I'm going to take the y value of the red function minus the y value of the blue function, right? So how I can write this in an integral is I want to sum up an infinite number of rectangles. So I'm taking the sum again from -2 to 1 of the top function, which the red was f of x, minus the bottom function, which was g of x, okay? That's what's going to give me the height each time, right? And then times that teeny tiny width or base of dx, all right? So if I write this integral -2 to 1, and I just plug in the equations, we can do that. F of x is 2 minus x squared minus g of x was x, right? So if it's calculator active, I'm done, right? Type this in, math 9, be done. If it's not calculator active, I need to anti-derive and then plug in my values, all right? And again, we're going to do both, but I'm going to do this one with setup only. So again, we're integrating on the domain, so from -2 to 1, and then we're doing the top curve minus the bottom curve. That's what's going to give me the height, and then the dx gives me the base of each little tiny rectangle. All right, first pause on your screen. Can you just write f of x and g of x in your notes for example 1, please? All right, we're back. So let's try some all the way through. It says set up the definite integral that gives the area of the region bounded by the given functions, and then find the area both with the calculator and without. So let's go ahead and start with the calculator. You can just look at my calculator commands here, and then we'll work it by hand together as well. So I've already typed in f of x in y1 in blue, and g of x is y2, and it'll be in red. And here's what the graphs look like. Okay, so I've got them graphed here. I want to find the area between the two curves. So kind of picture that shaded region there. So this is going to be integral, and then I need to see where they intersect, right? So to find an intersection, we go second trace 5 for intersect, and then we're going to get close to we'll do the a value first. We'll go close to the a value, and then we're going to hit enter 3 times, and that x coordinate is going to be my a value, right? So we're going to go from -2, and then we can do the same thing and get our b value, but this is going to intersect at x equals +2 as well. So that's going to be our b value. All right, so now if I take a look at this graph, I want to fill this in with a bunch of little tiny rectangles. And I want to go top y value minus bottom y value. So do you want red minus blue or blue minus red? We want red minus blue because red is the top, right? So that was our g of x function over here, the line, minus f of x, okay? So our integral is going to go g of x top minus bottom, f of x, dx, okay? So this is how we're going to type it in the calculator. I'm going to come to my home screen. I'm going to go math 9. From -2 to 2, then I'm going to open up another set of parentheses, and in g of x I had put into y1, so I'm going to go alpha trace number 2, I'm sorry, I put in y2, so we'll alpha trace number 2 minus f of x, which that one was my y1, so alpha trace, and grab y1, close that set of parentheses, and then dx. So I'm getting 10.6 repeating, right? Or 10 2/3. Okay, so that's doing it with the calculator. Now, let's say I didn't let you use a calculator on this one. So I first need to find out my A and my B. How do we do that? Well, we saw where they intersected, right? So let's set the two equal to each other. So I've got x squared plus 2x, go ahead and write this with me, plus 1. Equals g of x, so 2x plus 5. So I'm setting the two equal to each other. It's a quadratic, so let's get all our terms on the left side. So x squared 2 x's go away, and then minus 4, right? Equals 0. A couple ways we can do this, but I'm going to go ahead and do difference of perfect squares. So this tells me that my functions intersect twice, once at -2 and the other at +2, okay? So I know I'm going to go integral from -2 to 2. Now, without a graph, how do I know which one's top and which one's bottom? We'll pick any x value in this domain, any number between -2 and 2. So I'm going to pick like 0. Find f of 0 and g of 0 for me. Well, f of 0 is 1, g of 0 is 5, and 5 is bigger than 1, right? So g must be the top function, all right? So, and that tells me, okay, I need g of x, so 2x plus 5 minus f of x, so x squared plus 2x plus 1. All right, again, if this is not calculator active, I need to anti-derive and plug in, right? But let's make sure we clean stuff up before doing the calculus if possible. So let's do descending order here. Negative x squared. I have 2x minus 2x, so those are going to go away. And then I've got 5 minus 1, so that becomes 4. Positive 4 dx. All right, so now, look, this is already a lot easier to look at. So now let's anti-derive, so that'll be -1/3 x cubed plus 4x. And we're going to evaluate this at x equals 2 and -2. All right, I'll let you go ahead and plug that in and continue when you're ready to check your answer. All right, a little bit of arithmetic there gets us 32/3, which is the same as 10.6 repeating. All right, force pause on your screen. Can you go ahead and copy F and G for me? And then we'll try this one together. And notice you do have an asterisk, so this one's calculator active. All right, so let's take a look here. Let's take a look at Desmos. All right, so I've graphed f of x in green, g of x in purple. Notice that these graphs intersect 1, 2, 3 times. Do you see how you have two kind of different areas, right? So that first area, its domain is going to go from -2 to 0. And then the second one is going to pick back up at 0 and end at +2, right? Because again, my intersections are at x equals -2, 0, and 2. Okay, so I'm going to need an integral to represent both areas, because notice that which is on top and which is on bottom, those two functions, they switch, right? So for that first piece, I've got green minus purple. If I do top minus bottom. For the second piece, I have purple minus green. Okay, so let's set up our integrals. So I'm going to go integral. The first one, again, went from x equals -2 to 0. And for that first piece, I have green minus purple. So f of x minus g of x. When I subtract those y values, that would give me the height of each rectangle, dx. Then I want to add the integral from x equals 0 to x equals 2. And notice for that second piece, when I take a look at it, again, I'm looking at this piece now, I have purple, when I do top minus bottom, I have purple minus green. So that's g of x minus f of x dx. Okay, it's calculator active and make the calculator do the rest. So I'm going to go integral from -2 to 0, and show you how to do this on Desmos as well. And I can literally type in f of x minus g of x dx, so that part's 12. I'm going to do another integral from 0 to 2 of g of x minus f of x dx. That part is also 12, so my final answer is going to be 24. First pause on your screen, can you please copy the functions f of y and g of y for me? And then we'll do this one together. There is an asterisk, so it is calculator active. All right, so a couple kind of hopefully things you notice here is first, it's kind of weird because your functions are in terms of y instead of in terms of x. And maybe you see here, this black one doesn't even pass the vertical line test, right? So we've done is kind of tilt everything. So the problem is if I try to do these vertical slices of top minus bottom and try to fill this in with vertical rectangles, what we call cross sections perpendicular to the x-axis, that's all fine until I get here. That whole time I could do top minus bottom, green minus black, green minus black, green minus black, but right here we have issues, right? So that's not going to work for us doing it that way. So what if instead we slice our cross sections horizontally and move up instead of moving across? So if I did these, if I fill in with these kinds of rectangles, would that work? I think that'll work, right? Because you'll be able to have the same function on the right every time and the same function on the left. Here's what I mean. If I go ahead and take a look at, let's just pick out this rectangle. Okay, teeny tiny height this time. So instead of dx, I'm going to have dy. But take a look at its base. It would be whatever the x value is on the right minus whatever the x value is here, right? If each tick mark is 1, I think this base is 2, right? Because I would take 3 minus 1. So instead of going top minus bottom, you're going to go right minus left, okay? So that would be the case no matter what rectangle I picked, right? If I pick this rectangle, for example, this time the height's going to be a teeny tiny dy, but the base varies depending on which slice I pick, but it's always going to be the right x value minus the left x value, okay? All right, so let's go ahead and set up this integral together. So we've got the integral, and now let's shape this area. So there's my area, but now notice everything's going to be in terms of which variable this time? Everything's now going to be terms of y, so I need to make sure that my a and b are y values as well, right? So instead of taking the domain of the yellow region, I should be taking the what? I should be taking the range, okay? So how could I find the intersections without a calculator, without a graph? Yeah, set them equal to each other and solve for y, right? Maybe you can tell though my graph is a little bit pixely, but the range goes from -2 to 1, so that's going to be my a and my b respectively. Now instead of doing top minus bottom, I'm going to do what? You can do right minus left. Always go the larger number minus the smaller number, so you get a positive one, okay? So which one is the right function, f of y or g of y? That's going to be g of y, right? So I'm going to have g of y minus the left function, f of y, and then my differential will be a dy. Okay, so plugging this into the calculator is going to look like this. Integral from -2 to 1. Let's see, g of y was 3 minus y squared minus, and then f of y was y plus 1. And I don't think it's a bad idea to clean it up a little bit and write in descending order. So -y squared minus y, and then I'm going to have 3 minus 1, so that'll be a positive 2. Okay, so when you go to type this in the calculator, for the calculator, the x or the y, it's just a dummy variable, okay? You're going to antiderive and plug in regardless, and that's the computation the calculator is doing for you. So you can, go Math 9 here, you can take the time to put in y's, or I usually just do x's because it's just easier to grab that button. So I'm just typing in, you see I'm typing in the exact same thing, I'm just using x's, and should get a value here. So I got 4.5. And you will notice you should never get a negative answer when you take the area between two curves, because remember, whether you're doing top minus bottom or right minus left, that piece is always going to give you a positive value, right? Even if you take two negative numbers, as long as you do top minus bottom, you're still going to have a positive answer, okay? So no more negative areas, if you will. All right, I've got a quick little summary on the screen for you. Go ahead and write that down, and then I will see you all next time.